Hi everyone, I'm Theo. Talking about this new solver I've been working on called GeNIOS. Name is still a work in progress, but right now it is generalized Newton inexact operator splitting solver. But in essence, it's inexact ADMM. There we go. So the motivation for this is just how do you exploit more structure that's present in optimization problems? And if we look at some common optimization problems like Huber fitting, which is a robust regression problem, we get these constraint matrices that clearly have tons of structure in them. If we look at Markowitz portfolio optimization, which was mentioned in a talk earlier as well, again, we get this constraint matrix that has a ton of structure in it. And there's a question of like, can we use information that we as the user know about the problem to speed up the solvers? Many solvers, of course, force problems into a very standard conic form that has only a few kind of standard cones, and this can cause kind of an explosion in the number of variables. And of course, if you have a quadratic or a cubic subroutine in this solver, you're going to go from 4x the number of variables, might add 2 orders of magnitude to the solve time. And of course, this means it's hard to take advantage of problem structure if you're just putting everything into a sparse matrix. And so to go into one example for Huber regression, the details aren't super important, but essentially you have this pretty simple machine learning problem on the left, which is just your standard L1 regularized machine learning problem with kind of a different loss function. And then the equivalent quadratic program on the right is going to have this you're going to, instead of optimizing just over x, now you have like x and r and s and t and q. And so you start to introduce a lot more variables. You get this matrix where that A matrix, which is probably going to be a huge amount of potentially dense data, is in the upper left corner. And then everything else is this very sparse thing. So we'd prefer to solve this one if we know kind of a priori. So this solver, GeNIOS, kind of is motivated by this, and we construct it to solve general convex programs. We're using inexact ADMM, so we only actually need function, gradient, and Hessian vector product oracles for f. And the Hessian vector product can be approximate. And then we need function and proximal operators for g. Of course, this can be specialized to things like quadratic programs, conic programs, and then this kind of general form, what I call a machine learning problem, but it's a very specific type of machine learning problem. And we use an exact ADMM for this. So ADMM, I don't have time to give a full overview, but we solve 2 subproblems at each iteration. And what we're going to do is we're going to approximate these subproblems. So we're going to solve approximations to the subproblems. For the first subproblem, we use a second order approximation. The important thing here is first, it allows us to only need that function, gradient, and Hessian vector product in terms of our interface for f. But then perhaps more importantly, it means that this problem is a linear system solve. So we don't have to run like LBFGS. We don't have to do anything, kind of bespoke for that subproblem. We can just put it into linear system solve, and we don't have to assume that that subproblem has a quadratic objective because we force it to have a quadratic objective. And then we need an approximate operator or an approx operator for the second subproblem. But this is something that I won't get into that much in this talk. Then after we have this, we inexactly solve these 2 subproblems. And as long as we can control the error in these, it turns out that we inherit actually not only the convergence guarantees of ADMM, but actually the exact same rate of convergence. So theoretically, we don't really lose anything by doing these approximations. And so back to this, we can kind of look at, the Huber regression standard form or kind of the natural form on the left, the equivalent quadratic program on the right, and then figure out kind of, so first we solve like very standard, solve the equivalent quadratic program with exact subproblem solves, do the inexact subproblem solves, and then kind of look at the directly solving the problem on the left, which we do through this like machine learning interface. So for that, all we say is give us your loss function, give us your L1 and L2 regularizers, and we'll find the best linear model based on your loss function and these regularizers. And you can see it's basically specified with kind of 2 parameters plus a function that the user supplies, uses autodiff to figure out the first and second derivatives, and this is the per sample loss. And actually, if we supply the conjugate function to this, we can compute the duality gap for this particular type of problem. So perhaps instead of just looking at the primal and dual residuals, you would rather use like a very explicit duality gap and use that as your termination criteria, and that's something that we can do as well. Providing the conjugate function tends to be quite easy when you're dealing with a one-dimensional function. And then the quadratic programming solver just needs the problem data matrices and vectors, and this is easiest. While we supply a native interface, it's easiest just to use jump to supply these. And what we see is actually kind of surprisingly, we can easily get like a 30 to 60x speed up by using the non-native form, or sorry, using the more natural form of this problem versus using that extended formulation as a quadratic program. One other interesting thing here is if you look on the left, we're looking at both the dashed lines are the entire solves and the solid lines are the linear system solves. So when we go to a quadratic program, it actually, the overhead on top of the linear system is greater. And that is because kind of having a dense block and a sparse matrix is bad. And even for things like calculating the convergence criteria on this, we're not able to like use kind of, BLOS level 2 operations that have really, really fast dense matrix vector multiplies. Of course, this is Julia, so we can say, well, why don't we make a custom matrix type here? And I would say that kind of sounds like a lot of work. So it's easier if we can just specify our problems directly. The one other example I wanted to go through is this Markowitz portfolio optimization, which is just solving a quadratic program. The important thing here is the covariance matrix, which is the matrix that appears in the objective, is known to be diagonal plus low rank. And usually, kind of before you solve this program, you have the diagonal and low rank factors of this. So this is something that's part of the problem data. Of course, if you form this matrix, you form a dense matrix, and the solver has no idea that this is diagonal plus low rank. And this is clearly kind of a quadratic program just because it's quadratic objective and linear equality and inequality constraints. So there's a question of how do we take advantage of structure here. I'd say the traditional way, which I'm just glaze over in the case of time, but is to form an equivalent program. You introduce some new variables, very minor in terms of, in this case, we're actually not introducing a large number of new variables, but this isn't a step that most canonicalizers could recognize. This is a step that the user has to do. So you're kind of offloading the burden to the user to do this, even though you're getting a much faster solve. The Julia way is just saying, okay, well, I know that I can multiply with this matrix really effectively, so why don't I, use linear maps, turn F into a linear map, construct this operator, and then same thing for the constraint matrix, and do that. There's an even more interesting way, which is we can recognize that the set that we're dealing with is the simplex, and we actually have very efficient projections onto the simplex, which is the Z subproblem, which is essentially solved by a one-dimensional root finding problem. And essentially, the takeaway from that is it's really, really fast. So we provide an interface that allows you to specify this entire thing, kind of that what I talked about earlier directly. And with these 4 equivalent ways to solve of the original QP, the QP with fast operators, so that's using multiple dispatch, the reformulated equivalent QP, and then the equivalent convex program where we deal with the constraint set directly. And kind of might want to ask how these compare. And you get significant speedups as you kind of go from one to the other. So forming the matrix is a very bad idea. Projecting onto the simplex turns out to be a very good idea. Even being able to use custom operators, we found actually starts to really improve over solving the equivalent QP as you get to large problem sizes. Cool. And there's code and documentation up. Right now, it is not on the package registry, but it's there. There's the jump interface for QPs. And I'm hoping to expose more and more of like the kind of custom interface of the solver in jump as well. Thank you.